Yo, what's going on, guys?
Hey, hi Ashton, how are you?
Good. How are you, Ashish?
Yeah, I'm good. Good evening.
Good evening to you too. Mayamba, can you hear us? Hey, David, how's it going?
Hey, what's up? Yeah, I joined.
Yeah, appreciate it.
Yeah.
Trying to get a good turnout, so see what happens. All right. Figure we'll probably start at like 6:05. Okay, cool. I just saw your message, Mayamba. Basically, we're just gonna go over what binary search is. I'm sure most of you probably already know it, and then we're gonna just go through like 2 or 3 LeetCode questions, and yeah, that'll be it. I'm gonna try and share it to the teams as well. Not sure how it'll work. All right. So am I allowed to ping everybody? Is that allowed? Yeah. Okay. Yeah, good idea, Mayamba. I just pinged everybody in the Google chat. All right. So how many of you have heard of binary search before? Just by a show of hands. Or like put a little thumbs up. Ashish, you know it. David, I'm sure you know it. Based on the studying you've done. So it's a pretty straightforward algorithm. Yeah, so here's the agenda. I'm gonna go for an overview, then go through these 3 LeetCode problems, maybe a few more. So why use binary search, right? So here we'll take a look at linear search. And you can see kind of the time complexity. If you're searching for a number in a sorted array, like say you're searching for 3 in a sorted array, and it's just got the numbers 0 through 9, it'll take you can see 1, 2, 3, 4 iterations in this specific array to get to the third one. Whereas if you're searching for 8 in that same array, it's going to take you 1, 2, 3, 4, 5, 6, 7, 8, 9 iterations to get to that key if it's present, right? Now, if you compare that to binary search, it's going to be much faster, specifically for the 8, right? Because instead of having to iterate 9 times through every single element prior to 8, you're going to take the middle element, which in this case happens to be 4. You're going to compare that to 8, okay, which is our target. 4 is less than 8, so we can then eliminate everything, including and to the left of 4, or the index that has 4 in it, in this array. So in linear, right, you're kind of eliminating one, you're eliminating like one option at a time. Whereas in binary search, you're eliminating half of the remaining options for every iteration, right? So you check 4, which is the middle element, it's less than 8. So because of the sorted property of the array, you know that if 8 is in this array, it has to be to the right of 4. So we're going to eliminate 4 and everything to the left. Take the middle again, happens to be 7, still less than 8. So we're going to eliminate 7 and everything to the left of it. And then we find 8, and it only takes us 3 iterations. Same thing for 3 here on the left. We check the first one is 4. That's greater than 3. So we're eliminating everything, including and to the right of 4. Taking the middle of the remainder. Actually, I'm not sure if you can see my mouse. I'll try to get a pointer. Okay, yeah, here we go. So you're checking 4. It's greater than the key. So we're eliminating everything, including and to the right of 4. Now we have 0, 1, 2, 3. We're taking the middle element, happens to be 1. It's less than 3, so we're eliminating 1 and everything to the left of it, because if the array is sorted, 3 has to be to the right of it, right? Now we have 2 and 3. Check 2. It's not the answer. Eliminate 2 and everything to the left, and we only have 1 left, which is 3, and we got our answer, right? So in terms of big O time complexity, linear search is linear, obviously, because the worst case time complexity is that you have to look for like 9, for example. In this array, you're looking for the very last element, and you would have to iterate through every single element in the array to get through 9, right? So your time complexity would be big O of n, where n is the length of the array. You have to iterate through every single element. Whereas in binary search, you're eliminating half of the remaining options each time until you get the correct answer. So that's going to be O of log n time, which you can see the time that like the number of operations is much lower, especially as the input data size increases. So that's going to be a more efficient and faster algorithm. And yeah, so the basic algorithm, like I said, linear search traverses one element of the array at a time. So it's only eliminating one possible index at a time. Binary search checks the middle index, then can eliminate 50% of the remaining possible indices. So it's gonna be much faster. Here's kind of like the pseudocode for it. So you're gonna put a pointer at 0, call it left. So that's the first index. You're gonna put a pointer at right. It's gonna be the last index, or the length of the array minus 1. And while left is less than or equal to right, you're gonna calculate mid, which is gonna be left plus right, integer divided by 2, because you need to have an integer for list indices. And then if you're gonna check your array at index mid, and if that's greater than the target, then we know that if the target is in this array, it has to be to the left of the middle index, right? So we're gonna set our right pointer equal to mid minus 1. Otherwise, if array at index mid is less than the target, we know that if the target is present in our array, it has to be to the right of the middle index because of the sorted property. Again, you can only do binary search on sorted arrays. Therefore, we're going to set left equal to mid plus 1. Otherwise, if the array at mid is equal to target, or index mid of array is equal to target, then we're going to return the index mid if it's like looking for what index is this at, or we could return true if it's checking if a number is present in the array, or you could probably return any number of things, right? Depending on what the question is asking for. So for the first question, we got this LeetCode, it's just called binary search. So you can click on that to open up the link. I'm just going to share my screen on that. So let me know if you guys can see this. It's probably a little bit zoomed out, so I'll zoom in. How does that work? Give me a thumbs up if you can read it, or just put a message in the chat. Sheesh, it's good. All right. So I want one of you to unmute and try to give me the code for this problem. So Ashish, do you know Python? Do you want to try coding this?
Well, I haven't tried from a long time. Maybe I will face a little problem. I think so.
Okay.
Yeah.
All right.
Yeah.
So you don't want to try it? You want to? Maybe you can do one later. Okay, I'll show you like this one just because it's the first one, so that you guys get a feel for it. So left, I'm setting to 0. I'm just going to call it L. Oh, or I'll call it right. Make it more readable. Right, I'm going to set to the length of the array, which is going to be set to nums, or it's going to be called nums. -1. Oh, sorry, I didn't read the problem, but this is just a very basic one. So given an array of integers nums, which is sorted in ascending order, so it's sorted from lowest to highest, and an integer target, write a function to search target in nums. If target exists, then return its index. Otherwise, return -1. And then it says here, you must write an algorithm with O log n runtime complexity. Of course, the name is already binary search, but this right here is telling us that we need to use binary search. It gives us a couple test cases, and then we have to write an algorithm to determine the answer, right? So I set left to 0, that's the first index of the array. I set right to length of nums -1, it's the last index of the array. And then I'm just going to use a while loop, and the condition is while left is less than or equal to right. Here's what we're going to do. Okay, we're going to create a index. We're going to call it mid for the middle index. It's going to be equal to left plus right, integer divide by 2, and we're going to put left plus right in parentheses because we obviously don't want to integer divide one of them by 2 and then add it to the other one, right? And then integer divide by 2 instead of dividing by 2 ensures that we get an integer so that we can actually use it as a an array index or list index in this case. And then we're going to check if nums, which is our array at mid, is greater than target. All right, so this is the first condition. Can somebody either type it in the chat or yell it out? What do we want to do if nums at index mid is greater than the target? What does that tell us about nums at mid and our search so far? Oh, sorry, I didn't realize it was muted. Okay, so does anybody want to unmute and tell me what they know about, so we got this if statement here. If nums at index mid is greater than the target, what do we want to do, right? What does that tell us about the array? Does anyone want to unmute and tell us or type it in the chat? David, you want to put it in the chat or unmute and tell us? Right, so it's telling us if the target is greater than 4 or if the index is greater than whatever the target is, right? But so looking at this array that I just put right here, okay, we check nums mid. Let's say target is equal to 2, and we check this array right here that I wrote out. The middle index of this array, the value is equal to 4. So 4 is greater than 2. So what does that tell us about the array? Yeah, exactly. You take out 4, 5, 6, 7, because you know that if the target exists in this array because it's sorted, it's going to be on the left half. So to do that, all we're going to do is right is equal to mid minus 1. So now, if the other case is true, right? If nums at index mid is less than target, we're just going to do the opposite. So left is equal to mid plus 1. And then really there's only 3 possibilities, right? Either nums at index mid is greater than the target, it's less than the target, or it's equal to. So I'm not going to bother typing out elif nums at index mid is equal to target, right? I'm just going to put else because it's either greater than, less than, or it's equal to, right? So we know that else is suggesting that we found the correct index. So what are we going to do? We're going to return the index, like the question says, if target exists, then return its index. Otherwise, return -1. So for that last part, otherwise return -1. If it's not present, like what's going to happen, right? So say my target is 2, and I just don't have a 2 in here, right? I'm probably going to land on the 4 first. 4 is greater than 2, so we can eliminate all of these, right? Next, our array is like 1, 3. We're going to land on 1. So left is on index 0, right is on index 1. Mid is equal to 0. 1 is less than 2, so we're going to increase left. Left is going to be mid plus 1, right? Now, all we have left is left and right both on 3. So obviously, if left is 1 and right is 1, mid is going to be 1 plus 1, integer divide 2, 2 integer divide 2 is 1. So we're going to check index 1 again. Nums mid is going to be equal to 3. It's greater than target. Our target is 2, right? So right is going to be equal to mid minus 1. Now, right is equal to 0, and left is equal to 1. So our while condition is no longer true because it was while left is less than or equal to right. Left is now greater than right. So we're going to break out of the loop, and what we do is just return -1. Right? So if our target is in nums, we're going to get to this case, we're going to get to this else case, and we're going to return the index of it. Otherwise, we're going to return 1, just like it says. If target exists, return its index. Otherwise, return -1. So let's run it, see if it works. All right, beat the first 2 test cases. Let's submit it, see if there's any edge cases we missed. And it doesn't look like there is. Right, so looks like it could be faster. Maybe we could optimize it somehow, but it's not a big deal. All right, so let's go on to the next one. So where are we? Oh, so -1 specifically is just for that specific problem. So like this specific problem says, if target exists in the array, then return its index. Otherwise, return -1. So yeah, so maybe another question would be like, if the target exists, then return true. Otherwise, return false, right? So we could do the search insert position, but it's pretty similar, right? Sort of just okay, so this one is like the same thing, you're returning the index if the target is found. And if not, you're returning the index where it would have been if inserted in order, right? So this one is like extremely similar to the last one, right? So I'm just going to copy paste it. Okay, so same thing. Left is equal to 0, right is equal to length of nums minus 1. And then we're going to have our while condition, calculate the mid, compare it to the target over and over again. So I think this much is fine, right? But we have to figure out how are you going to return the index where it would be if it were inserted in order, right? So do you guys have any ideas on how we would do that? No, she says no. Okay. All right, so let's just change this to mid. We're gonna return mid either way. Let's run our code and let's see what happens, right? All right, so the first test case, phi was in there, right? So it worked. All right, for our second test case, we got the wrong answer. 2 was not in there. Ended up outputting 0 when it was expecting us to say 1, okay? Because 1 is less than 2, 3 is greater than 2. So if we were to insert this in order, 2 would be at index 1, 3 would be index 2, then 5, then 6 would be index after that, right? So how can we figure out how to solve this one, right? What do you guys think are some ideas? Mayamba, do you have any ideas? David, any ideas? All right, so one thing we could look at is where would it be in this test case, right? Because that's what the test cases are for. The examples, that's what the examples are for. So you can figure this type of thing out. So looking at this one, we got the target is equal to 2. Obviously, like I said, it would be inserted at index 1. So how do we make sure that we keep track of that index 1 to return it in the case that we don't get the result that we're looking for, right? So in this one, if we just trace this binary search, okay, we can do that pretty easy by just inserting a print statement. We're gonna print left, mid, and right for every iteration, right? So when we look at the output, first iteration, left is on 0. Of course, it's where it starts. Right is on 3. That's where it starts. Mid is on 1. So after this, immediately, right is shifted to 0. After that, we're comparing 1 to 2. 1 is less than 2. So our 1 is less than 2. So our left is incremented to mid plus 1. So now our left is at index 1. Our right pointer is at index 0. So left would be correct here, right? Left is the index that we would be looking for. It happened to be on 1 after everything was said and done, right? What about case 3 though? So this one, target is 7. Obviously, it would be inserted at the very end of this array because currently the max of this array is 6. So if we were to insert 7, it would be at the end, right? So length of the array right now is 4. After the insertion, it would be 5. So target would end up at index 4, right? But if we trace the program's execution, we're starting with left on 0, mid on 3, or sorry, right on 3, mid on 1. We compare index 1, 3 to 7. 3 is less than 7. So we're putting our left pointer on index 2. Okay, so we have 2, left on 2, right on 3, mid on 2. We're comparing 5 to 7. 5 is less than 7, so we increment our left one more time. Both left and right are on index 3, so mid is on index 3 as well. 6 is less than 7, so what do? We increment left again. Only at this point, left is greater than right, so our condition is no longer satisfied for our while loop. So the loop, we exit the loop, right? So in this particular case, left at the very end is also equal to our expected result, right? So if we break out of the loop, we return left, right? Is there a chance that we get the right answer? So for these test cases, it happens to work, right? But if we submit and run it against some more cases and some edge cases, oh, it actually works. So why does that work, right? Let's go back to the test cases. Okay. So in this one, example 2, we kept decrementing our right until it was set on 0. Left and right were both on 0. It was less than the target, so left was incremented to 1. That happened to be the correct index, and we returned left once we broke out of the loop. On this one, 7 was greater than the max of the index, right? So we were shifting left more and more to the right until left and right were both on this index. And then when we incremented left one more time because 6 was less than the target, the condition was no longer satisfied, right? Left was no longer less than right because right was on index 3. Left got incremented. We broke out of the loop. We returned left, and that was our output, right? That was what we needed. So that happens to work there, and that's just kind of like using this print statement is giving you an example of how you can use print statements to debug programs when you're not exactly sure what the solution is, right? Then we got one more question. So this one is searching a 2D matrix. So were there any questions about the last problem before we go into this next one? All right, so we're gonna start the last one. This one is searching a 2D matrix. So you're given an m by n integer matrix called matrix with the following two properties. Each row is sorted in non-decreasing order. The first integer of each row is greater than the last integer of the previous row. Given an integer target, return true if target is in the matrix or false otherwise. You must write a solution in big O of log m times n time complexity. And it's giving us some examples here of a couple matrices. So what do you guys think would be some, or maybe the main challenge with this problem right here? No, I don't think it would work if we returned right. Here, I can open that last one up. All right, so on just using this one as an example, that's just gonna write it out. Right, so left is starting here and right is starting here. Target is equal to 2. Right, so the first thing we're going to do is calculate mid. Mid is going to be equal to 0 plus 3. Integer divided by 2. 3 integer divided by 2 is going to be equal to 1. So we check at index 1. 3 is less than 5, right? So we're going to set right equal to mid minus 1 according to our algorithm, right? Because if nums at the index mid is greater than the target, right is equal to mid minus 1. So now right is on this pointer, or right is equal to this index pointing to this index. We calculate mid again. 0 plus 1 integer divided by 2, we get 0. So we're going to check this index. Oops. 1 is less than 2, right? What happens if the thing is less than our target? If nums at index mid is less than our target, well, then we increment left. Or sorry, left is equal to mid plus 1, right? So mid is at 0. Left is at 0. Left is now going to be shifted over to 1, right? So left and right are both pointing at 1 right now. So then this is going to be like the final iteration. We're going to compare, so 1 plus 1, integer divide 2, of course we get 1. We're going to compare 3 and 2. 3 is greater than our target. Our target is 2. So right is going to equal mid minus 1. Oh, sorry. So mid is also on index 1. Right is now equal to mid minus 1. So we're shifting right over here. This condition is no longer true, right? Because we're only looping through this as long as left is less than or equal to right. Now left is greater than right, so the loop terminates. If we were to return right here, right is equal to 0. It's pointing at index 0 of the array. If we were to insert 2 at index 0, we get this, right? So then that's obviously not a sorted array. We would want it insert 2 at position 1. So yeah, that's the reason why you can't return right here. So yeah, David, you're right. The challenge here is that it's 2D, right? So I'm sure we all know matrices from math in first semester. So we got this integer matrix. So everything in the matrix is going to be integers. It's called matrix. The size of it is m times n. It's got the following 2 properties, right? Each row is sorted in non-decreasing order. And the first integer of each row is greater than the last integer of the previous row. So basically, every single row is going to be sorted, so we know we can binary search it. But also, we know that this, if these are our 3 rows, we know that 10 is greater than 7, right? The first element of row 2 is greater than the last element of row 7, or sorry, of row 1. So 10 is greater than 7, right? So nothing greater is going to be in the next row compared to the previous row. So when you look at this one, you can think of it in 2 ways. So look at this matrix right here. It's basically just a sorted array. So we have 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, 60. If you just iterate through it one by one, the array is it's increasing, right? It's in increasing order. So you can really just think of it as a 2D array, or you could think of it as first you want to find which section it's in, or rather which row it's in, and then search that row. So there's kind of 2 approaches that you can take. Do you guys have any preference for one that you want to try? I want to see someone else try to code this one. So give me some ideas for how to approach this problem. Ashish, Mayamba, David, anyone have an approach for this problem? She says, trying to understand. Mayamba says, I have no clue how to do this, lol. Okay, fair enough. So do you guys understand like the basic binary search algorithm, how it works so far? Yeah, for the most part. Okay, so how do you think you would apply that to this problem here? All right, so you're in the interview. The interviewer pulls this one out. You know how to do a binary search. What's kind of like your gut instinct? What's your first step in approaching this problem? Trying with I and J, Ashish. So you're saying like use
Like I don't know about too much because I haven't learned this topic too much. But maybe like we know like I into J, so we can try with that something. I think so.
So you mean like 2 pointers or like a nested loop to iterate through
Yeah,
the
like if we want to go on particular, like position, then we have to follow I into J if I'm right.
Yeah, like we need 2 pointers so that we can go not just
Yeah.
across the columns, but into the rows. Okay, yeah, that makes sense. David, you say it's multi-dimension matrix array in Java. Do you know how to apply that here? I'm not sure about that in how that's different in Python versus Java. Like here, I'll show you an example of the syntax. You tell me if this is similar, David. So for this one, it's called matrix. So yeah, I'll just print matrix index 0, right? So when I print matrix index 0, it's printing the entire first row of the matrix, right? Now, if I do it like this, print matrix index 0, it's just printing the first element of the first row of the matrix, right? So Ashish is saying that we can use this notation to cycle through the matrix using like 2 pointers, I and J, right? So he's saying for I in range length of matrix. I don't know why my indentation is not right for some reason, but for J in range length of matrix 0, print the indentation is weird for some reason, but it works. Okay.
May I say something?
All right, you want to use row and column?
So
David, here.
like Ashton.
What's up, Ashish?
So if I'm like recalling, I don't know, maybe it will be correct. So can we do something like that? Like if we are trying to check for first row, then making first row uh, uh, constant and changing the call value, and then for second row, like this concept.
Okay, so searching, doing a binary search within each row.
I don't know too much. Like I'm just like making the first row concept, then try checking for every column, and then changing the row to second, and yeah, it's kind of a loop.
Okay, yeah, I see what you mean. So here, just looking at this one, right? Combining what David and Ashish said. So we're iterating first with the first loop. We're iterating through the rows. The second one, we're iterating through the columns of the rows. So we're going to go for the first row, so 0, right? We're going to iterate through each column of it with our nested loop, right? So we're going to go 1, 3, 5, 7. Then we're going on to the next row. The row gets incremented, column gets set back to 0. Okay, we're going to 10, 11, 16, 20. Row gets incremented, column is set back to 0. 23, 30, 34, 60, right? So when we go through that and we just print the matrix at index row, index column, just printing it, we do in fact get like an in order traversal of the nested array, right? So using that, how can we use that in a binary search? Ashish, you're saying that we should figure out which row it's in? Like iterate through like, I mean, we could compare the first element of each row, right? and figure out from there. If we're looking for 7,
Yeah, kind of. I was just trying to like compare each element with the every element, and then where it is just match in the uh, I think index.
so like in terms of like the whole array of arrays here, like right, like the nested structure, you're going to iterate through and say you want to find 3. You're going to check like the middle, and you know that one's greater than 3, so you're going to just search like this part. Is that what you're saying? Using the row and column.
No, I was not doing with the binary search. It's just an ordinary method, like checking every, like if our target is 3, then checking on every, like every index. Oh, sorry, on every position, and wherever it is matches. If it's matched, then just saying it's true, like printing out the
Okay.
value. Yeah.
Okay. All right, let's try that. So matrix at row column equals target, return true. And I don't know why my indentation is messed up. If it's not there, return false. Right, so let's see if that works. All right, so it did actually work for both of these. Let's submit it and run it against some more test cases and see what happens. Oh, wow, it actually worked and was very fast. That's crazy. Okay. You're right, though. It isn't binary search. It's just a normal linear search. So if you really want to use like binary search and show off your binary search skills, right? You can implement that. I'm actually kind of shocked that it was so fast. Wow.
Me neither,
No explanation. All right, but if you want to solve it as a binary search, I'll show you that because it is a binary search question. So David's saying do the left, right, mid thing again. So how are we going to set up our left, right, and mid in this one, right? So before we were doing length of the array -1 for our right index and setting the left index at 0. Can we do that again here or no? What do you guys think? Rows times columns -1, says David. All right, for the right pointer, and then we'll set the left as 0. Right is equal to, all right, how do we get the rows times the columns? Well, we're going to take the length of matrix is going to give us the rows. And then the length of one of the rows is going to give us how many columns, right? So we're going to do length of matrix plus, or sorry, times length of matrix just using the first row. So we're going to get 3 rows, 4 columns. 3 times 4 is 12 -1. That's going to be our last one, right? So then we're going to binary search between it. And again, like we're looking at this array right here, the array of nested arrays, and we can see that it's sorted, right? But the problem is that it's split into multiple arrays. So we can't just quite as easily iterate through it, right? So we have like one sorted array with the maximum of 7, followed by another sorted array with a maximum of, or sorry, minimum of 10, maximum of 20, followed by another sorted array with a minimum of 23, maximum of 60, right? So what we could do is find some sort of way to iterate through this as if it's a like a linear array. Do you guys have any ideas? My cat's trying to drink my water. So David, you came up with the rows and columns idea. How do you think we would kind of iterate through the rows and columns in this problem? All right, so we can start by left is less than or equal to right, or right is less than or equal to left. All right, so usually you want left is less than or equal to right. I mean, you could also probably do while right is greater than or equal to left, right? And it'll have the same effect. We're just going to do left is less than or equal to right. I don't know what's going on with my indentation. Maybe it's because I'm so zoomed in, but it's tripping me out. All right, so then I think earlier you said just do the same thing where we calculate mid, right? So mid is equal to left plus right, integer divided by 2. How do we find mid? So we calculate it just like that, the exact same way, right? Or at least we can try this. Because, you know, like we've said, kind of established that this array, if you look at it holistically, it's essentially just one array, right? It's one sorted array because the maximum of the first row is going to be less than the minimum of the second row. The maximum of the second row is going to be less than the minimum of the third row. So we just look through one element at a time. It still retains that sorted property, even if it's like made into a 2D matrix or like segmented into lists within the greater list, right? The question is like, if we find this mid index, how do we map it to this 2D array? Does anybody have any ideas? All right. David says mid value is equal to matrix mid integer divide columns index mid modulo columns. All right, so let's try that, right? So if matrix, we're just going to do like our basic binary search structure. So like in the last two, the array was called nums and we calculate mid, right? So then we have a target. If nums is greater than target, what do? Well, if nums at mid is greater than the target, then we know that if the target is in the array, it has to be in the left half. So we set right equal to mid minus 1. But in this case, we can't use nums mid, right? Well, first of all, because the name is matrix, but we can't use this either because it's 2D, right? So David is saying to use matrix mid integer divide columns, mid modulo columns, right? And he's saying we should store that in a variable called mid value. So if we look at this, we have the matrix, the row, and the column, right? So what's David cooking up for us here, right? So first row, mid integer divided by columns. If we just try this, well, I'll just write the whole thing out first, and then we can debug it after. Okay. L if mid underscore value is less than target, left is equal to mid plus 1, else return true. If it's not in there, return false, right? Let's run that, see what happens. Oops. Okay, got a little bit mixed up. Columns is just going to be equal to length of matrix 0. Okay, we just need the number stored, right? All right, so David's solution worked once we stored columns because we were referencing something that had been assigned. Okay, so why does it work? We're also going to submit it, test it against some more test cases. And what do you know? It works perfect, right? So why does it work, right? So we're looking at matrix. This is like the big part right here. Like this is the big piece of code that made it work. Everything else, like, is pretty basic, pretty straightforward, right? We have the same thing as always. We have the same backbone of our binary search. So something to think about here is how you have to take like the same algorithm and adapt it to the problem that you're solving, right? So we still have left set to 0. We have right in a little bit of a roundabout way set to the last index of the array. Then we have our while left is less than equal to right, mid is equal to left plus right, integer divide 2. We have if mid value is greater than target, then right is equal to mid minus 1. You know, this is like standard binary search right here. Okay. This is going to be in like the majority of your binary search problems. So what David did to solve this particular one is he said that the mid value is going to be equal to matrix at the index mid integer divide columns, mid modulo columns. David said he's heading out, take it easy. All right, so the row is going to be mid integer divide columns. How do we know that this is right? Let's print left, right, print left, mid, right, run it, okay? All right, so first, left is on the 0th item in the array, and right is on number 11. So 0, 1, 2, 3, if we just count as this as like a regular linear array, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So right is pointing to the last index. Mid is 0 plus 11, integer divide by 2, you get 5. So 0, 1, 2, 3, 4, 5, it's on the 11. The target is 3. So we compare the 11 to 3. 11 is greater than 3. What do? We set right equal to mid minus 1. So right is now equal to 4 right here. So mid is going to be equal to 2. 0 plus 4, integer divide by 2. We get 5 here, right? So we're going to check 5. If 5 is greater than the target, right is equal to mid minus 1. That's true. 5 is greater than 3. So we're going to set right to 2. Or sorry, 1. And we end up with mid on 0. We compare 3, right? 3 is left than, or so less than the target. So we increment left to be equal to mid plus 1. Now both left and right are on 1. So of course mid is equal to 1. We check that index and it's equal to our target. So we return it. So the reason this worked is because David came up with a solution where we calculate the mid and then we interpret it as a 2D array, right? So mid, for the row, he's saying mid integer divide by columns. We know we have 4 columns, and on the very first iteration, mid was equal to 5. So 5 integer divide by 4 is equal to 1. So we're not going for the 0 index column with 1, 3, 5, and 7. We're going for the 1 index column with 10, 11, 16, and 20. Then he said we need to use mid modulo columns to iterate through the columns, right? So we know there's 4 columns. And our mid is equal to 5. So we're going 5 modulo 4 is 1. So that's giving us 11, right? Because 11 is the 1 index element of the second row. So the first iteration looks like this, right? Once you do all these calculations, that's equal to 11. We think of this matrix as just a flat array. Looking for element 5, 0, 1, 2, 3, 4, 5. So we get 11, right? So David has just translated that into this different way of looking at it, where he iterates through each row individually, column by column, in order to just like iterate straight through in order, despite using despite using a matrix instead of a flattened array, right? So that's pretty much it for this one. Do you guys have any questions? No. All right. Well, it's 7. So if you guys don't have any questions, then let's call it a day. Hope you guys enjoyed. Hope it was useful. Cover some other algorithms later on in other weeks, and yeah, take it easy. Good luck on exams, and see you guys around. Yeah, no worries. Thanks for coming out. Hope it was useful. What's up, Ashish?
You have time for 5 minutes?
Yeah, what's up?
So I was just trying to get clear. So like for Python, so like are you practicing from the for first sem?
Yeah. Just like
And yeah.
I just learned it in first semester, and then I've just been watching like YouTube videos for the data
So
structures.
okay. Oh, so you're doing now data structures and algorithms.
Yeah.
Okay. Yeah, and in the next sem, now sorry, in January you have break, or are you continuing with third sem?
Yeah, I have a break. What about you? Are you in
Yeah,
computer
yeah,
or
me same.
Sydney? You have the break? All right.
Yeah, also.
I think that's better.
Yeah. And are you trying to get any job or something?
Yeah. Do you have co-op or what?
No, I have pop, but it's after third sem.
Yeah.
Same as you, I think so.
Yeah. I'm gonna try to probably just work on my portfolio and then try to
Okay.
get a
And
co-op